Hi students, today we will look at airport pavement design using the Canadian Department of Transport method. So here we talk about we look at pavement for different classes of airports, airport classification and runway pavement design using Canadian Department of Transport method. So here we said there are many principles that are common to the design of both airfield and highway pavements. However, there are several distinctive features. The most important is in the design philosophy. The priority of highway design engineers is to understand or assess the effect of vehicular traffic upon the pavement. While airfield designers do consider the effect of aircraft on pavements, but the priority of design involves the effect of the pavement upon the aircraft. Next, we look at magnitude of loads considered. In highway, maximum axle load of 8,170 kg or equivalent single wheel load of 4,085 kg is considered. Airport pavements are designed for equivalent single wheel load, also known as ESWL, of the critical aircraft that is supposed to use the runway. For example, Boeing 747 has a total weight of 353,000 kg and its equivalent single wheel load is equal to 37,000 kg. Remember, under the FAA method, we talked about the total weight. We said that it's splitted between the nose and the main gears. Then the nose gears take care of 5%, while the other gears take care of 95%. So here, the equivalent single wheel load, because you have to convert the wheel load of all aircraft under consideration to that of the design to be equivalent to that of the design aircraft. So here we say since wheel arrangement known as landing gear of different aircraft is different, ESWL is to be separately calculated. Next, we look at tire pressure values. It plays an important role in the design of pavements. For highway pavements, 7 kg slash 7 kg per cubic 7 kg per centimeter square is considered. For aircraft, it varies for different aircrafts. For example, Boeing 747, it is 12.04 kg per centimeter square. Next, we consider geometric section of pavement. Runway width ranges from 18 meters to 45 meters. Since the shoulders are unpaved and running engine can stuck in any loose material, so the design consideration is that the farthest of engine on the wing should remain over the pavement. So for large aircraft, the farthest engine is 13.5 meters, which is equivalent of 45 feet away from the longitudinal axis of the plane. On both sides, it becomes 13.5 multiplied by 2, which is 27 meters. Hence, 45 meters is enough width for runway pavement. Next, we look at considerations in the airfield pavement design. The rapid development of jet aircraft in recent years has had a profound effect on the pavement design concept. Jet engines are easily damaged by debris sucked into the air intake. Hence, design of shoulders and adjacent safety area and extended runway length considers to make them resistant to erosion from jet blast. The pavement must be resistant to the effect of fuel spillage and heat, since the spillage may cause softening of the asphalt binder. Type of load is another factor which affects the design of pavement for jet aircraft. Some jets are equipped with tire having pressure up to 400 pounds per square inch. Such pressure necessitates high quality pavement to withstand the punching effect of the tire. The bicycle landing gear has resulted in channelized traffic. Next, we look at types of pavement. We have rigid pavement. A rigid pavement comprises either wholly or partly concrete construction, which can be plain, reinforced, or pre-stressed, and in which distributes the aircraft loading to the subgrade by means of its high flexural stiffness. Flexible pavement. A flexible pavement is composed of bound or unbound granular materials. It distributes the aircraft load primarily through the shear strength of the paving material. Cement-bound granular bases beneath bituminous surfacing makes pavement quite rigid in their early years. This type of construction is also treated as a flexible pavement for design and evaluation purposes. Next, we look at composite pavement. These generally these generally the result of various strengthening and maintenance overlay. They may comprise of flexible on rigid construction, rigid on rigid, which is multiple concrete slab construction. So for composite pavement, when we have more than one type of pavement type, it becomes a composite pavement. We can have flexible on rigid and we can also have rigid on rigid, but we don't have rigid on flexible. So it is either after constructing a flexible pavement, we now have an overlay of another flexible, or we construct rigid and have have an overlay of a flexible, or we have rigid and overlay of another rigid, which is multiple slab construction. Next, we look at choice between rigid and flexible pavement. In general, concrete is preferred where there is likely to be venting of fuel. Remember, we said that the fuel can dissolve the bitumen. That is fuel spillage of lubricating oil and hydraulic fluid, jet efflux gases from slow-moving high-performance jet engines, or areas subject to locked wheel turns. Then the choice of flexible pavement. The absence of joints in flexible pavement gives them a better riding surface for high-speed operation than most types of rigid pavement. On an unpredictable subgrade which is liable to long-term shrinkage or heave, a flexible pavement will generally be the best option. This is because a flexible pavement can cope with greater movement and remain serviceable. It can also be more cheaply and quickly overlaid to rectify the loss of shape. We look at structural design life. Under structural design life, rigid airfield pavement lasts for 30 years, while flexible airfield pavements are designed for about 20 years. Next, we look at methods of design of flexible air pavements. We have the Corps of Engineers CBR method. We have the Federal Aviation Administration method, FAA method. We have the Canadian Department of Transport, which is CDOT procedure, and the Institute method. We also have ACN, PCM method, as given in 1983 edition of the Aerodrome Design Manual, Part 3, published by the International Civil Aviation Organization, where ACN is aircraft classification number, PCN is pavement classification number. Next, let's look at ICAO airport classification. So here we have airport type, we have basic runway length, minimum, maximum, and minimum. We have width of runway pavement for that airport type. Then we also have maximum longitudinal grade. So here you can see for the airport type A, the maximum runway length is 2,100 and the minimum still 2,100. So the range is between 2,100. So we have the width of the runway 45 meters and the maximum longitudinal grade is 1.5. For B, you can see the minimum is 1.5 meters, while the maximum is 2,099, and the width is 40 is the width of the runway is 45 meters, while the maximum longitudinal grade is 1.5. So you can view for other airport types here given on this in this table. So we look at the code number, the code number for each airport, and then the equivalent single wheel load are given. Tire pressure are also given here. So let's look at an example. It says an airport B3 would have basic runway length ranging from between. So let's look at that of B3, the airport B3. We can see this is airport A, this is B. So we have B3. The runway length is 2,099. So let's see if it's what we have there. An airport B3 will have basic runway length ranging from 1,500 to 2,099. Of course, you can see it ranging from 1,500 to 2,099. Then what else? Single wheel load capacity of 27,000 with a tire pressure of 7 kg per centimeter square. So go back and verify and see for that same airport set of B3. So the code is 3. So when you come to 3, you can see it has equivalent single wheel load of 27,000 and tire pressure of 7 kg per centimeter square. So next we look at the Canadian Department of Transport method. To determine the thickness of flexible airfield pavement, a method was developed by Canadian Transport Department of Transport. It correlated the load carrying capacity of a runway pavement with plate load test. This investigation was done by N.W. MacLeod. An empirical equation was developed as shown below. So this is the empirical equation where T is equal to K log P over S. So let's see what those terms means. You can see we have T, in which T is the thickness of the gravel material. K is the base cost constant. We read it from figure 1, the first graph. Then P is the gross wheel load K in kg, while S is the subgrade support value as obtained using figure 2, the second graph. So this is the first graph. This first graph, you can see what we have here. Here we have the plate diameter in centimeter. Then here we have perimeter area ratio, P over A. Then these lines here, these ones here, these lines, vertical lines here are for plate diameter in centimeter. Then these lines here, these inclined ones on the graph, are the deflection in centimeter. You can see deflection 0.125, 0.25, 0.5 up to 1.75. Then on the left, we have 0.1, 0.0, 2.0, 3.025. And what do we have here? What are we reading from here? We are trying to estimate the ratio of the unit subgrade support at deflection D for the bearing plate of any diameter over unit subgrade support at 0.5 centimeter deflection for 75 centimeter diameter plate. So The next graph we have here is the one of a base cost constant over the bearing plate diameter in centimeter. So let's look at the steps. One, we have to compute the radius of contact of the wheel, where A is equal to the square root of W over P pi. So here you can see step two is compute the perimeter over area ratio. So here we have P, which is the perimeter over the area. And you know that of the wheel. So the perimeter is pi d from mathematics, and our area is pi d square over 4 from also the area of a cycle. Then with this, if we able to, we can simplify this to be 4 over d. Then step 3 is compute the value of the unit subgrade S for the given diameter of the plate and use stress at the given value of deflection. So once we're able to have P over A value, we can now get it from the table, from that first graph. So from the first graph, once we have the value of S, this smaller s, we can now get bigger S by multiplying smaller s by d square over 4. Then we compute the value, which is the fifth step, is to compute the value of the thickness after plugging in or substituting the value of K as read from the figure. So in the second figure. So once we're able to get the value of K, we put it in and get the value of T. So let's look at an example. Here it says design a runway pavement for a wheel load of 27,000 kg with a tire pressure of 11 kg per square meter. In site investigation, a plate load test has been conducted with a plate of 75 centimeter diameter that showed a bearing pressure of 2 kg per centimeter square at a deflection of 0.5 centimeter after 10 load repetitions. So next, you can see from the formula we have A is equal to square root of W over P theta. W over P pi. So here we have in this, we will know that we have from the question, the load is 27 kg. So we substitute it in over here. We have the pi is given, that is tire pressure. P is given as 11 kg. So we substitute it for P, and the pi is a constant, which is 3.14. So once we're able to find the square root of this, we have 28.5 centimeter. Then next, we have to get the perimeter over area ratio, which is P over A. Remember, we had it as 4 over D. So we substitute it. We already have our D is equal to, because this is the radius. So radius is always half of the diameter. So it's going to be 2 times the radius to give us the diameter. So that's why we have 4 over 2 times the radius, which is 28.5, and we have 0.07. So next, which is step 3, compute the value of the, we have to get small s for the given diameter of plate and use stress at the given value of deflection. So let's look at the graph. From this graph we have here, this is what we do. We look for 0.7, 0.07 we have here. And remember that our radius, we have 28.5. We multiply by 2, it's supposed to give us 57. So it's supposed to give us 57. So when we come to this graph, we go to where we have, can see 0.04, here 0.05, 0.06, 0.07. So we move up a bit, close to this 45 to 60 for the plate diameter. And what we have from our calculation is 28.5, which is 57. So 57 is close to 6 here. So here we also need to note our deflection. From our question, our deflection was given to us as 0.5. So we go back to our graph, then try to trace 0.707 up to where we have 57, and then we draw a line there, and also a line across where we have zero point 0.5 deflection. So it will intersect with the vertical line. Then from there, we can now read it on the left. So let's look at what we have done on the, here we have, you can see we moved down to 57 here. It is close to 60 from where we have 0.07. Then from here, we have deflection of zero point 0.5. So if we're able to read where they intersect to the left, we have 1.2. So from the graph, you can see x is equal to 1.2. So the x we're looking for is 1.2 times. From the question, recall that we were given our bearing pressure as 2 kg per centimeter square. So what we need to do is to multiply 1.2 that we got from the graph by the 2 kg, which is 2.4. So it says the next step is to compute the value of the total support, which is the bigger S, and is equal to smaller s by d square over 4 from the formula we had earlier. So this will be equal to, the smaller s is 2.4 multiplied by pi is 3.14 multiplied by 57, because our d is 57, then squared over 4. So x, capital X, is equal to 6,121.1 kg. So next step, which is the fifth step, is to compute the value of the thickness. So the thickness T of the pavement is equal to K log P over S, in which T is the thickness of the gravel material, K is the base cost constant, then P is the gross wheel load, then S is the subgrade support or subgrade value. So from here we have, this is the formula. So from the above figure, we have to look at the next graph so that we can be able to obtain the value of K. So from this table, you can see we have our plate diameter was 57. So from 57, we move up and touch this graph we have here, and then move to the left. So once you're able to touch it from 57, because this is 50, this is 60, then this is 50, then we have 75. So 57 will fall in this region. That's why we're able to mark it red, and then move it to the left. We have 130, because this is 100, this is 125, this is 150. So around 130 or 130 something. So if we're able to go back, we'll see that from there our K is 138. So that I got it from the graph. We now say log P is the load that was given to us initially, and see where we had P as 27,000. So 27,000 over S, we had our bigger S today, which we said is 6,121.1 kg. So we substitute it back, and then we have a total of 88.95 centimeter thickness of pavement.